tutors. On this live telecast, I'm going to teach you chemical equilibrium. As I've said earlier, I'll be teaching you chemical equilibrium. So let's go there now, please. Let's go there. Now, looking at this, okay, looking at this, we have chemical equilibrium. I'll be taking it line by line. Okay, there are some that I will have to try and you see now chemical equilibrium. Okay, chemical equilibrium is defined as the state of chemical system where there is no observable change in the property of the system with respect to time. Now, when the forward reaction is the same thing as the backward reaction. Let's look at an example here. Now, look at this. At the start, you can see what happened here. We have a glass here. Okay, at equilibrium, everything is circulating around. Okay, that's just by the way. Let's look at this. How can we know that something is in chemical equilibrium when the reaction is reversible? How do we know that reaction is reversible? This is how we know. Look at here, for example. This reaction is very, very reversible because you can see an arrow going forward and coming back. Okay, it means the reaction is what? Is very, very reversible. Just like what we have here also. Okay, just like this. Those are just some examples. Now, under equilibrium, we have something we call dynamic equilibrium. Let's see this for example. This is dynamic equilibrium in a reversible reaction. Dynamics means it's moving. So reversible reaction is in dynamic equilibrium when both forward and backward reaction are what? Occurring at the same what? Rate, producing no net change in the concentration of the reactant or product. It means the concentration of the reactant or product are not changing. Okay, so that's just I'm going to give you the PDF format of this book so that you can read it at your leisure time. But what I'm here to explain today is this. We are starting from here. Equilibrium constant. Now, looking at the equilibrium constant, how do we go about that? Look at this reaction, for example. Looking at this reaction, okay? Now, in a reaction like this, we have A with a small a, B with a small b. Now, this A with a small a, what does it stand for? What does it stand for? It stands for the mole. It stands for the mole of that A in that particular place. If you look at it very well, it stands for the mole. Now, if I give you an example, let's look at an equation for example. Look at this equation for example. This iron now is having 3 moles. Water is having 4 moles. This is having just 1. There's an invisible 1 in front. This hydrogen is having 4. That's just an example there. Now, let's look at this, the general format. How can we now put equilibrium constant? Now, is a law. The equilibrium constant means the products. You can see the product here. What is given us from the product, okay, divided by what we have in the reactant. That's what we call equilibrium constant, which is K. What we have in the product divided by what we have in the what? In the reactant. That's the equilibrium product. Now, if the reaction involves solid, let's get that very well. Liquid in solution, whether the reaction have a solid or liquid in the solution, the equilibrium constant is denoted by Kc, that is C for concentration, Kc, indicating what? Concentration in moles per dm cube. But for gaseous reaction, Kp is used because P is used to indicate what? Pressure. Let's take some examples here, please. We have an example here. Write equilibrium constant as calculation. Example here. You can see there's an example. We are being given CO2 gas plus H2 gas in a reversible reaction, giving us H2O gas plus CO2 gas. Now, they gave us the concentration of CO2 to be this. Now, H2O to be this. Hydrogen to be this. And CO to be this. How do we now do it? We go for our equilibrium, determine the equilibrium constant for the reaction. Very simple. Let's take it as an example. I will write it out as CO2 gas plus H2 gas to give us H2O, okay, plus CO gas. Now, if you want to write the equilibrium constant here, how do we go about it? Now, we have to see our Kc, okay, will be equal to, now we can see the product here. The product is this and this. If you look at it very well, the product is this and this. How do we now do it? Very simple. To get the product, we have to say H2O, this H2O now, H2O, okay, you now put it in a bracket. The mole is 1, so we are not raising it to any power because the power will be the mole. And another one, CO, okay, which is a gas. It doesn't have any mole. We are leaving it like that, okay. Now, divided by the reactant. So this is also having 1 mole, so there is nothing on it. So we have CO2. Since there is only 1 here, it doesn't have anything here. And what? Hydrogen. And if you look at it, they gave us the concentration from the question, and this is it. They say CO2 is 0.75, and that's how, this is what I've just written. That's how that H2O is what? 0.36. That's how they put it here. Multiplied by CO is this. You can see it as right there. And hydrogen, which is this. You can see it there also. Okay. And we have this, which is 0.75. And you can see it there also. So after the calculation, this is what we got. Okay. Now, I would like to talk about the condition, because this one will follow the same format. You can see another one. So I will give you the PDF format of this so that we will not waste our time. The PDF format, you will read it, go through it. If you have a question, you can ask me any questions, okay? Since I will leave the link of my WhatsApp, the WhatsApp group, you can join the WhatsApp group for better understanding of all these things. Now, there is a rule of this game. We call it Chatelier's principle. What does he say? He said the principle states that if a chemical system is in equilibrium and one of the factors involved in the equilibrium is altered, the equilibrium will shift. This is the main deal, please. The equilibrium will shift so as to annul or neutralize the effect of change. Yeah. So as to annul or neutralize the effect of the change. Now, concentration, and we have pressure of the reactant and product. Let's talk about it one after the other. The first thing is temperature. So first thing we have there is what? Is temperature. So temperature is the first thing. So temperature, number 1. So we have temperature. How does temperature work? We have something, reaction we call endothermic, and we have some reaction we call exothermic. If you have a reaction like this, which is reversible, and it gives us C with small c plus a D with a small d, just like that. It is what? Now, if they say it is endothermic, it means the change in enthalpy is equal to positive. When it is positive, it is endothermic. Now, this is what always happens here. Increase in temperature, okay, increase in temperature, what does it do? We now shift the equilibrium from the middle, because the equilibrium is here naturally. We now shift it to the right. Okay, increase in temperature, we shift the equilibrium to the right, which means it favors the production of more of the product. Because this is endothermic. This is what? Endothermic reaction, where heat is being gained into the system. Heat is being gained into the system. So when you have something like that, increase in temperature, okay, we shift the equilibrium to the right. Or we say increase in temperature favors the, okay, forward reaction. Favors the forward reaction. That's what increase in temperature does. favors the forward reaction. It means it favors more production of this, more production of this. When it is endothermic, let's put that in our mind. When it is endothermic, okay. But if it is not endothermic, it will reverse will be the case. Now that's for temperature now, okay. So second one, let's go for pressure, because the second one is let's go for now. The second one is, we have pressure, we have concentration. Now talking about concentration, that one is straightforward. Let me even look at what is here. Effect of temperature. The effect of temperature depends on the types of reaction, as I've said, okay, whether endothermic, which is positive, or exothermic, which is negative. For an endothermic reaction, an increase in temperature will favor the forward reaction, and the equilibrium constant will increase. That's just the case. This is an example of endothermic reaction. Another one, so increase in temperature will favor the production of this, and production of this. Increase in temperature. Okay. Now, when we want to talk about pressure, I want you to remember something. That of pressure now. Effect of pressure. I want you to remember something about pressure. What I want you to remember is this. Effect of pressure always affects gases. Effect of pressure always affects gases. So if this is a gas, for example, this is a gas, okay, this is also gas, and this is also gaseous. What will happen is this. If this one consists of 2 mole, for example, if this C is 2, let's take an example. Let's take Haber process. In Haber process, we have nitrogen gas reacting with hydrogen gas in a reversible reaction to give us ammonia. So what happens in that scenario? What you think will happen is this. When it gives us ammonia, this is 2, this is 1, so we have to put 2 here. 2 times 3 is 6, so we have to put 3 here. So it is, ratio is 1 here, so it's 1:3:2. Now, in the reactant, this is the reactant, and this is the product. Now, increase in pressure favors where we have the least mole of pressure of the gas. Okay, now increase in pressure. Okay, favors the side. Okay, increase in pressure favors the side, okay, with the lowest mole of gas. Mole of gas. Let's look here now. 1 plus 3 for the reactant. What is the mole? We have 4 moles. Here, for the product, what do we have here? We have just 2 moles. Now, this side has the highest, this side has the smallest. Okay, so increase in pressure will favor this side because there is only 2 here, and this place in the reactant we have 4. So increase in pressure will favor where we have the lowest mole of gases. That's what will happen to where we have increase in pressure. The smallest mole of what? Of the gases. Okay, so let's take for example. Pressure depends on 2 major factors. So pressure affects only gaseous constituents. There must be a change in volume of each constituent from reactant to product. Let's take an example here. Now, an increase in pressure will favor the direction with a decrease in volume. I said that. Thus, equilibrium shifts to the right, considering the reaction below. Look at this. we have 2 moles here and we have 1 mole here. So 2 plus 1, you have 3. Here we have only 2 moles. So this ion have the lowest amount of mole. This is where increase in pressure will favor. Increase in pressure will favor where we have lowest amount of mole of gases. Mind you, look at this for example. Look at this. Here now we have 3 moles. Here we have 4 moles. This is a solid. We are less concerned about that. So it means in this side we have only 4 moles. Now here, this is solid. We are less concerned about that. We also have 4 moles because it's a gas. So gas and gas, 4 moles and 4 moles. Increase in pressure will have no effect. You can see pressure will have no effect because iron, which is this, and iron 2 or 3 oxide, okay, which is this, are both solid. This iron and this are both solid and won't participate. Okay, now only 4 volumes, only 4 what volumes are left in the reactant. You can see the 4 volumes left in the reactant, sorry, and product. Hence pressure has no effect because this is 4, this is 4, it has no effect. But mind you, when we are talking about the pressure here, because this is gas and this is gas, that's why we can add it up to make 3. 2 plus 1, 3. Now because this one is gas, so pressure is mainly for gases. Pressure is mainly for gases. Effect of concentration now. This one is just very simple. An increase in the concentration of the reactant favors the forward reaction, and equilibrium shifts to the what? To the right, and vice versa. So if you increase the concentration of this, it favors this side. Increase the concentration of this, it favors this side. It's as if you want to prepare your eba and you want to prepare more eba, you need more garri and hot water. When you increase concentration of garri and water, you prepare more what? Eba. Let's take an example here. Consider the reaction represented by the equation below. We have one here, we have another one here. Okay, it's reversible. So we have 2H1. This negative, this exothermic. Let's look at the volume first. We have 1 volume here, we have 1 volume here. Add it together, making 2. We also have 2 here. We are very sure pressure will not have any effect on this, either increase or decrease, because they have the same volume. Now, which of the following takes place when the temperature of the reaction vessels is decreased? When the temperature of the reaction vessels is what? Decrease. Now, temperature decrease here in favor of the forward reaction. Remember I told you that in endothermic, effect of temperature depends on the type of reaction. So when it's endothermic, okay, for an endothermic reaction, an increase in temperature will favor the forward reaction and vice versa. Okay, now if it is decreased, it will be vice versa. Now this is exothermic. An increase in temperature is supposed to favor this place because it's exothermic, but they now decrease will not be the opposite, it will favor this side. You can only know one so that you can remember the other ones. Which of the following takes place when the temperature of the reaction vessels is decreased? So when the temperature is decreased, this place will be favored. Now the gas condense, that's a lie. The yield of hydrogen increases. Where is hydrogen? No. The concentration of the reactant remain constant, that's lie. More of the hydrogen iodide decomposes. No. The yield of hydrogen iodide increases. E is the correct answer. We increase the yield of this because the equilibrium is shifted to that side. Let's look at another example. This is another equation. This is gas, this is gas, this is gas. Okay, so 3 plus 1 here making 4. So we have 4 volume here, we have 2 here. Okay, now increase in pressure will favor this side with the smallest volume, favor this side. So right from there, now in the reaction above, the effect of decrease in pressure on the equilibrium position will lead to, now we increase pressure, it will favor this place. If we now decrease pressure, it will favor this side. Increase pressure favor this side, decrease in pressure will favor this side. Okay, so what do we now do? They now said in the reaction above, effect of decrease in pressure, it favors this side. So let's look at the option. Decrease in the amount of oxygen produced. Decrease in pressure will increase everything here. So this is not correct. Decrease in the amount of sulfur 4 oxide produced. This is sulfur 4 oxide. It is increase in the amount, not decrease. Increase in the production of sulfur 6 oxide. This is sulfur 6 oxide. Okay, it's not increased, it's decreased. With what? Increase in pressure. No change in the concentration of both the reactant and products. No effect on the equilibrium constant. That's a lie, because now in the reaction above, the effect, you can see no effect of what? Equilibrium constant. Because increase and decrease in pressure does not have any effect on what? Equilibrium constant. That's just by the way. So here we have another thing here. What is the effect of using vanadium oxide as a catalyst? It just speed up the rate of reaction, because that's what catalyst does. Speed up the rate of what? Of chemical reaction. So if you look at this very, very well, we still have some other things that we have to go through there, and I would like to speak them one after the other. Now look at this. This is the industrial application of chemical equilibrium. I will give you that also. I will give you the PDF format of this so that I can read it. The Haber process. You can go through that one. I will give you the PDF format. Okay, people that are in my WhatsApp group, I will give them the PDF format so that I can read it. So if you also want to join my WhatsApp group, I will leave the link in the description below so that you can join the WhatsApp group for better understanding and teaching. This is Brostedlori's theory. There's another thing there. So let's now look at some other questions. Equilibrium is said to be attained in a reversible reaction when, this is just some questions. Consider the reaction represented by the equation. Look at it. Write an expression for the equilibrium constant. Equilibrium constant is always the product over the reactant. But mind you, this thing will be the power. These two here you can see SO3. And the 2 is the power. Here also we have the SO2. This 2 is the power here. Oxygen has only 1. That one is the power, okay? That's the equilibrium constant. We are using P because it's a gas. I've explained that before. So equilibrium constant of the pressure. That's what it means. So this is another thing. This one is talking about energy profile. I think I will make another video on energy profile very soon. I will make another video on energy profile. Consider the equilibrium reaction below. You can see the amount of sulfur oxide produced will increase if, now, sulfur oxide, how can we increase it? They didn't show us if it is endothermic or exothermic, no problem. But if you decrease the pressure, it will be this, because 2 plus 1 will be 3. This is the side with the more volume. You need to decrease the pressure. The pressure is decreased, so A should be the to yield more of sulfur 6 oxide. This is sulfur 6 oxide, sorry, sulfur 6 oxide. So it's either you increase the pressure to favor this, you can increase the pressure, or if it is exothermic, a decrease in temperature for an exothermic. Yeah, this exothermic, they didn't put it there, but it should be minus. It should be minus. That's how it is. So my people, I will send the PDF of this thing. I will send it to you people on the WhatsApp group so that you can enjoy it. Thank you and God bless. See you next time. God bless you and enjoy yourself. Thank you and God bless.